I wanted to share what I have been working on the past few months. So here is nonlinear projection-based model order reduction using the interpretable machine learning. So let me just start with by saying that in current engineering, for the design and validation process, we still use experiments. And the thing about experiments is that these are often too expensive if you want to go to the original prototype, because if you want to modify something to see how the experiment acts with this modification, then you'll have to build either another prototype or modify that part of the prototype. So they, as you can see at the end of the animation, they also often use digital replicas that are mainly based on data-driven models, so they're purely based on data. And what we want to develop is some sort of digital replica that make use of current computational models, such as the finite element method, the finite volumes, which are often very high fidelity models. However, they are often very expensive as well. So what we do in order to cope with this is to use reduced order models, which will give us a much faster solution with a higher fidelity than the ones that are based purely on data. So, as I said, if you don't want to work with a huge prototype, you can build a very small prototype, in this case, for instance, of the ACNET body. However, if you want to go ahead and do the pre-design of the optimization of the geometry, you can also do a traditional CFD run. In this case, to do the CFD turbulence model, it takes 240 cores with more than 10 hours per run. So this is, of course, too computationally demanding, and you cannot do it if you want to solve it for many configurations. So today I'm going to show you how I managed to develop a reduced order model that is taking only 8 cores, so 30 times less computational resources, and just doing these simulations in 2 minutes. So going back to the full order model cost, whenever we need to solve for many times, it is often too computationally expensive. So it pays off to do what we call an offline stage or training stage, where you will set up some simulations, gather the data, and build a reduced order model that takes way less time than the full order model. And the way that these reduced order models are classified, they can go from non-intrusive, which has no access to the PDE, often are based purely on data-driven models, and you have the ones that are fully intrusive that has total access to the PDE, and even you have to modify the PDE. So the way that these models work is that you input some parameters mu with some Reynolds number, you pass it to the reduced order model, and this reduced order model will give you a state approximation or some quantity of interest. Some examples of non-intrusive reduced order models comes with something that is called the proper orthogonal decomposition that we'll be talking about, plus some interpolation model, and you can also have the dynamic mode decomposition, and you can have something in between these both, which are called highly reduced order models, which require partial PDE access. Where 2 examples are the one that you try to infer the operators of these reduced order models from the data, and the other ones are called physics-informed neural networks that uses the equations in the training stage. And the ones that I have been working the most in my PhD are the ones that are totally intrusive and are projection-based reduced order models based on the Galerkin projection and the LSPD projection. So let's talk about the full order model. We could be talking about an structural dynamics case. We could be talking about a model problem that has a moving discontinuity, like the 1D Bullius equation. We could be talking about a 3D compressible Navier-Stokes or even a compressible Navier-Stokes. And the 3 of them can be fully discretized by the use of finite element, by the use of finite volumes or finite differences into a fully discrete residual formulation, which can be also seen as a vector-wise residual component that is often millions of degrees of freedom or has millions of degrees of freedom. And the way that you minimize this residual is by a Newton-Raphson or something of this sort, where you will solve a linear system of equations that is huge. And when I say it's huge, as I said before, it's something that in the industry is of tens of millions or sometimes billions. So this often requires the use of high-performance computing. What we aim with the reduced order system is to, or the reduced order model, is to find a reduced representation of this full order system by projecting it into a much smaller subspace. the way that, in such a way that what we're going to be solving instead of a million by million degree of freedom problem is a problem that is maybe 5 by 5 or 10 by 10. So let us go ahead with an example. We have a wind turbine model, nonlinear dynamics in a structural model where we set up an offline retraining stage. We define a transient surface load that varies with the time. It has some training amplitudes. And then from these training amplitudes, we can take a look to different snapshots on the training configuration that will look something like this. And these are nothing but some vectors at some time instances and some different parameters that you can put together or stack into snapshots matrix. And most likely you will never only take like a few of them, but you most likely want to take a few more points, not only 4, in order to build a snapshots matrix that will be of size of the degrees of freedom times the number of samples that you would take, such that the next point is to try to approximate this snapshot by means of only few modes, and this is done by the truncated singular value decomposition, where you will gather these left singular vectors, you will gather the first n modes. These n modes will be nothing but some spatial modes. Here I am plotting the first 6 months of the wind case, and if we keep in mind this operator and we go back to the original state, in order to reproduce this state in a much smaller dimension, we will project it into this linear subspace, such that we want to do is we want to find a smaller representation of U with terms of this operation by projecting with this operation. So we will find some smaller Q, which will be of size 5, 10, 20, or so. And in order to recover this small coefficient, you will have to just multiply by the operator phi. We have this autoencoder-like compression using a linear EOD. Now, if we take a look into the offline, if we want to build the reduced order model, this was the offline part where we build the operator phi. Now, what we need, or what I want to explain to you here, let me just accept quickly Charlie. So the question is, once we define this operator, how can we build a reduced order model out of this? So how can we find a different Q for a new parameter that we have never seen? And let us go back to the original full order model. And the first thing that you can do is just go ahead and plot this approximation that we have of the bigger state. And we will have a problem that now is looking for only Q unknowns, which are very small. But you can see here that the problem is still rectangular, and a simple way to make this problem square is just by projecting it with the same operator, transpose. And this is called the Galerkin projection, and is often optimal for the cases that are symmetric positive definite, so where the operators like the Jacobian is symmetric positive definite, such as the structural mechanics case, and you will end up with a very small system of equations. So we have a huge improvement in terms of what we are solving. So let us go back to the problem. Now let us define some testing amplitude, something that the training of the reduced order model has never seen. In this case, I am not varying that much, but the input has different testing amplitudes than the one on the training. And if we build the reduced order model, let us pay attention to the table on the top. The full order model was solving 18,000 degrees of freedom. We managed to solve 7 degrees of freedom, and then we are getting a relative error that is 0.14%, and the time that we are taking for solving the system is 24 times faster than the 24,000 times faster than the original one. However, if we take a look into the wall clock time, which is something when you start the simulation to the end of the simulation, we are only winning 2 times the in a speed up with respect to the full order model. And this is because we are looping through all of the elements. And for that, let me go back to the reduced system, and let's just pay attention to the right-hand side. The way that we build this projected version of the residual is by looping through all of the elements. And I prepared a small video for this. Maybe it's better if we explain it like this. You have a finite element model, so this is already the projection version for the model, which the phi transpose R is going to be it's going to be defined as a sum of all the elements. You will find a small basis for each element, which is of the size of the number of modes times the degrees of freedom of your problem. And you have your corresponding right-hand side of this elemental quantity. And the way that you build up this small right-hand side is by looping through all of the elements. So you can imagine that the cost of going through all of the elements here is still scaling with the high-dimensional model, because we need to loop through all of the elements. So in this very simple case, it's not that much, but in the industry, you can be talking about something that that could be of the order of 50 million of degrees of freedom, well, 50 million of elements. So what you want to find is a subset of elements and assign some positive weights such that you will approximate this phi transpose R by means of only some elements by the use of hyper-reduction techniques. One of them is the empirical method, and as I said here, now you will only select some elements. You will go to these elements and you will assign the same operators, but you will have this new weight, and you will perform exactly the same operation that you were doing for the projection-based reduced order model. However, you will do it only on the new selected elements, which will be much less than the full order model or the reduced order model complete. So as you can see here, we have the structural dynamics problem by means of only 85 elements instead of looping through 14,000 elements. We still have the same error, and now we have a speed up of whole clock time of 60 times the original. So we are 30 times faster than the original reduced order model, while still having the same results and accuracy as the one that we have. So, given said that, I just wanted to say a very few words about another projection. When you are moving towards problems that are not non-symmetric or that are governed by transport problems, the Galerkin projection that I was talking about is no longer the optimal one, and you have to do something that is called the least squares Petrov Galerkin, which minimizes the residual in the L2 norm, and you will end up with a system that is of the same size of the Galerkin. I just wanted to mention you that I am no longer going to use in my presentation the Galerkin projection. And I want to introduce something that is called a phenomenon that is called the Kolmogorov-Engwick barrier. So for the first problem, as I told you, we were using 7 modes to reproduce a problem that was very accurate. However, I have worked with much more complicated reduced order models. For instance, the dynamics of the thermodynamics of a motor, where we needed 44 modes. However, if you go more and more complicated special patterns, you will have to use more modes for that. So this is something that is called the Kolmogorov-Engwick barrier. It is nothing less than you will need to use more and more modes in order to reproduce this with linear POV. So one very good example or problem that we can use in order to develop or to see this Kolmogorov-Engwick barrier is the Burger's equation. I'm going to present a very simple 1D Burger's equation. We have mu1 as our parameter in the left part of the domain, and mu2 that affects the right-hand side. And you define a computational domain, you discretize in time and in space, and then you define your domain, your time domain as well. And you can discretize by the use of the finite element, the finite volume, or finite differences, and depending on your scheme, you will have much more or less the same accuracy. It depends on the order of accuracy that you want to obtain. So let us take the finite element 1 as our case. And then now I'm going to define the parameter domain that I'm going to be training and testing. So the training points are 9-point grids on mu1, 3, mu2, 3, so 3 by 3 grid. And we will then be testing on some other points. So in order to show you what is the effect of each of the boundary conditions, let us freeze mu1, mu2, and let us change mu1. And we see that what we change is the left velocity in our propagating or shock propagating problem, and you can see that the velocity changes as the initial condition changes. If you now freeze the velocity and change the source term, you will see that it has an effect on the tail, and the effect is highly nonlinear. In order in order to see the different dynamics of the problem, we set the 9 different training simulations, and we can see that the problem is highly nonlinear, and we will most likely have the Kolmogorov-Engwick barrier. So if we perform the POD on 4,500 snapshots, we see that the energy that we have in the decay is pretty much very flattened. So better said with examples, if we set up a projection-based reduced order model of the size of 9 modes, we see that in blue we will have the PROM with a very bad approximation. Then if we go to 40 modes, which is already a lot of modes, we are now tracking the discontinuity. However, we have these oscillations, and these oscillations are not because of the scheme, but rather because of the approximation of the POD. And it is not until we go to 160 modes that we have a fair good approximation of the original full order model. So this is, as I said, the Kolmogorov-Engwick, and this can also be seen as an, let's say, limitation of the linear manifold in some problems. So I took a problem where we have this like chip or Pringle, if you know the Pringles trajectory in 3D, that of course if you fix your modes to be of dimension 2, this will set up a basis that lives on 2 dimensions. So the best linear approximation that you can do with 2 lives on the same subspace as the linear manifold. So you cannot do better than this line, right? So one of the first nonlinear methods that was proposed in order to cope with this, which is not exactly a nonlinear method, but rather a piecewise linear methodology, is that you can set up multiple bases, multiple 2D bases in this case. So we set up, for instance, 4 linear bases, and then we make the union such that we can approximate the trajectory in a much better way than only using 1. If we use that and plug it into the projection-based reduced order model, we will see that if we take 20 clusters that give us an average of 17 modes, and we compare these 20 clusters with the red one, which is the global with 17 modes, we can see that it is doing quite a better job than the original one. It has some spikes on the solution, which is a problem that we have to cope in the local POD, but I'm not going to go into the details for now. Now, there's another nonlinear, and this one is only nonlinear approximation, which is the quadratic approximation that takes let's say the 2D space and folds it into a quadratic manifold in such a way that the approximation of U equal to VQ now depends also on the Kronecker product of Q, so it's like Q squared, such that we have a much better approximation of the quadratic manifold. In this case, the trajectory was meant to try to fit a quadratic manifold trajectory. So, if we go ahead and plug and do a quadratic projection-based reduced order model, we see that for 21 modes, we win something with respect to the red one. However, it is not the best winning. It's better, but we cannot say it's huge, or the improvement is huge. We want to do best than this. So for that, I would like to introduce you to what I've been working on the past months. So this is building on top of something that Professor Farhad has been working, which the first part that we have to consider is we do the first SPD, the traditional one. So let me here mention that I am saying n dot, difference to n, because now n dot I am considering that has a lot much more modes. So we would like to keep something that was of the order of 10 modes, and we will have. And for that, the first thing that we can do is just split the basis into one basis that will be called the primary mode basis, and another ones that will be the secondary mode basis. In such a way that the primary modes have only 10, and the other one could have, for instance, 100. And I just want to let you know that to this point, I am just splitting. I am not introducing any error. It is exactly the same as if we were doing the traditional linear reconstruction. I am just splitting these two and splitting these two, so it's a sum. However, what I would like to find now is some nonlinear function that give us a representation that depends on Q and give us Q bar, so the secondary modes coefficients that we were not taking into account. where Professor Farhad started with approximating this by an artificial neural network. The good thing about the artificial neural network here is that it does not scale with the size of the full order model, but rather with the size of the number of nodes, which is very small, 10 to 140. And in order for you to have an idea of what we win here is that we only need to project the state dimension or the displacement field by the phi transpose. We will obtain very few coefficients. From this nonlinear map, we will obtain the other coefficients in such a way that in order to approximate this state variable, we will sum the contribution of this q bar that was obtained by q. So we never need to solve for the unknowns here because we have a magic function that gives us from q bar, which is not magic, it's an artificial neural network. The way that we train this nonlinear map is by doing the same snapshots capturing, building the same or a different snapshot solution matrix that you will then project into the phi transpose and phi bar transpose to obtain a snapshot matrix of pairs of inputs and outputs, which are defined, for instance, Q is defined by the small coefficients Q1, Q2 until Q number of samples, Q bar 2 till Q bar number of samples, oh sorry, it was here, such that this will serve as our inputs in our training nonlinear map, and this will serve as our outputs in the nonlinear map, such that, as I said before, we will train this nonlinear map, for instance, by the use of an artificial neural network. So this was done by Professor Farhad. A very simple way to see this is that with the linear manifold, we were only able to project it into the subspace. However, with this phi bar times the nonlinear, we can shift this linear solution into the manifold such that we will be able to blend it into, or to, let's say, try to fit it into our nonlinear manifold. So let us go into the projection-based reduced order model, a little bit more into the details, not much more, but one of the projectors that we use instead of phi transpose, we use the Jacobian, for the LSPG, we use the Jacobian of the finite element plus the derivative of our approximation. And as you can see, we will need, or we will make use of the derivative of the nonlinear map that I was talking about. So this can be done by automatic differentiation using a neural network. And if we plug it into our projection-based reduced order model, we see that we are using, in green, you have a global P-ROM with n, so modes equal to 17. And in blue, we see that we use the same 17 modes as primary and secondary 79. But I have to remind you that the problem that we are solving is of size 17. So the 79 secondary modes is like a post-process per se. Now, you can even go further than 17 modes, so I was just trying to show you that it matches of the piecewise linear manifold. By reducing it even further, I reduce it to 5 and 91 secondary modes, and we still have very good relative error. So the question here that arises is the ANN the only and the best nonlinear approximation that we can do? Is there something that can do better than automatic differentiation for the derivative? Is there, is the ANN interpretable enough for us to use it? So I will introduce something that you may be already familiar, which is the radial basis function interpolation, which is nothing. It looks actually like the finite element linear basis where you have a sum of number of points times some weights that are evaluated. These points are evaluated in a function that is often a Gaussian or a multi-quadratic. I will talk a little bit about the properties of these functions later. And this function can be reduced to matrix form in the following way, which is just a vector matrix multiplication. And let me just show you a brief example of the interpolation. So let us say that you have your true function of x defined like this, and then you have some training points, as I was telling you, and with the RBF you will try to fit your best approximation possible to these points. So once you have this, the nonlinear closure map that we have, so the definition of this compact kernel for our specific nonlinear function that depends on Q will look like this. I will go into the details of what is this later, but I just want to tell you that we have a first proposal that has analytical expressions that is not a magic map, and it's very well defined in the literature. And we also can make use of something that is called a Gaussian process regression, which is, let's say, the probabilistic part of the RBF. Actually, it uses RBF in order to produce this mean posterior. However, the good thing about this is that from your training points, your GPR can tell you which is the confidence interval of your approximated quantity. So you have something that tells you, okay, I know that in here, I am very sure about the approximation, but maybe here in the middle, you either have to give me more points or retrain me to be better, to fit better there. But as you can see, these are two different proposals. One has the probabilistic part. You can train the optimization model with the machinery of the probabilistic part, or you can just simply do the deterministic one. But as you can see, the two equations are exactly the same because they use the posterior mean, which is the interpolator. Now, let us go a little bit into the details of what is our new nonlinear map. So it is a vector matrix multiplication. This is the vector of evaluated quantities that I will go into the detail, and this is some matrix that you have find that is it's a matrix of weights, similar to the weights of the neural network. So let us go and define this vector. You have some basis functions that you will, once you have your data, let's say that we have a new training point Q star, you will do an evaluation of this Q star minus Q1 of your training data, Q2, Qn, and you will evaluate it into some already defined kernels, which can be a Gaussian, multi-quadratic, an inverse multi-quadratic. And this kernel often look like this, and the thing that you need to solve for is which is the best pick of your smoothing parameter or shape parameters, and also which is the best kernel to use, for instance. Once you define this once we have defined this, we can go ahead and say, okay, but how do I find for the weight matrix? And for that, we need to solve a linear system. It's very easy. So I want to go very deductive. The matrix K here is exactly as the vector, but this is only with the training data points. So Q1 minus Q1 will be 0, then Q1 minus Q2, Q1 minus Qn, and that for all of the training points. And if we even want to go more and more deductive, the real problem that you will set up is you will also add some regularization in the diagonal, and then this is the matrix of training points that you have, so the Q bar that I was talking about. So you solve a problem that is of size of the number of samples times the number of samples. So this is something that is often very easy to solve, because the radial basis functions have some properties that gives you a symmetric positive definite matrix, which is cheaper, let's say, or easy to solve. And now you will have as weighting matrices beta 1, matrix of weights that is of size of the number of samples times the secondary modes. So once you have the beta points here, the weights, we can go back into our predictor and let us define the predictor again. I'm trying to be repetitive here just to see that this beta, just to say that this beta is something that you pre-compute offline. And offline, when you want to do the prediction, you will only have to go to your databases, and for the new Q point that you will have to do the difference in some Euclidean norm. You evaluate the radial basis function for that point with another point till all of the points that you want from your training data set. And then you will end up with an approximation that looks like this, where, as you remember, I was telling you for the LSPG projection, we will make use of this derivative of the nonlinear map. The good thing here is that there is no numerical derivative, there is no automatic derivation, but rather there is an analytical derivation, or a differentiation, sorry. which is of the following form. I'm not going to go through the details, but as you can see, the only thing that changes in this analytical derivative is the derivative of the kernel. So this improves a lot the condition of the matrix, the condition of the Newton-Raphson, and I want to go to a little bit more complicated problem to showcase the RBF and the GPR against the ANN by going to the 2D case Bulwerk's equation with the same input parameters mu2 and mu1. However, we will now have two moving discontinuities, not only one. As you can see, we have one along the x-axis and one along the y-axis. And in order to make it easier for you to understand the plotting instead of doing 3D plots, I'm just going to do a cut in the x direction and in the y direction. I'm just going to plot it like this, in the x direction, in the y direction. As you can see here, it's like the discontinuity moving along the time. So for another time distance, it shifts. For another one, it shifts. But it remains on the same cut plane. Now, let us go ahead and talk about the construction of the training data. So we have the same parameter domain as the 1D case. So we have 4,500 snapshots. Then we build a thin SVD. We keep only 5% of the data. And the traditional projection-based reducer model will give us 95 modes, which is a lot. And for the nonlinear P-ROM, the one that I'm talking about, we're just going to take 10 as the primary modes and 140 as the secondary modes. What we want to do with this 10 plus 140 is to do an accuracy that is comparable with a traditional reducer model of size 95. So I just want to make a comment that we built out this data, the data sets for the ANN, the GPR, and the RBF for this example are completely the same. And the way that I build the nonlinear map is, for instance, with the ANN, I based myself on a paper that was already built on the POD ANN, which was using a multi-layer perceptron, so an artificial neural network fully connected with 6 linear layers using the LU activation function. We split the training data set into 90% of training, 10 validation. We use a mean error for the loss function. The implementation is done in PyTorch. This is taking only 20 minutes. Whereas for the GPR, we use a kernel that is a composed kernel of a constant, which is like a signal variance, times some matern kernel, which is kind of like a Gaussian-like kernel, plus some white noise. So this is like to analyze the problem. And we scale the input, etc. We solve this by using the motor already present in scikit-learn with some optimizer that is already predefined. So this training optimization time was taking a little bit more than the neural network, but this is case dependent and data dependent. And for the RBF, we can see that I will do a much simpler training. So I will take 4 different candidate kernels, and I will do kind of like a grid search and then optimize this in a brute force, such that it is taking only 13 minutes. However, let us go and take a jump into the ECSW, so the hyperreduction, how it impacts the number of selected elements. So for the traditional HP-ROM that we have 95 modes, we see that we take 6,000 number of elements, selected elements, whereas for the ANN, GPR, and RBF, we're on the ballpark of 1,500. So it is 4 times less than the traditional HP-ROM. And if we go and take a look to the qualitative results, so I am plotting here, as I said, the cut on X and Y, and I am here comparing only the HP-ROM, which is the one in yellow, against the HP-ROM RBF, which is the one in blue. And as you can see, with only 10 modes, we are doing pretty much even better than the traditional one with 95. So if we go ahead and now compare the ANN against the GPR, which is more or less the RBF as well, we can see that we're doing a very good job. We are matching the same accuracy as the ANN. And if we go to, let's say, in my experience, the most complicated point, which is the one that it yells like kind of in the middle of everything, and we compare the 3 new ANN, GPR, and RBF, we see that the only part that they kind of struggle is at the end. But it is fair to notice or to mention that the traditional HP-ROM was also doing some weird stuff there. So if we want to improve that, we will just need to keep more secondary modes. So let's go into the quantitative results and comparisons. We were solving a problem that was 125 degrees of freedom with 60,000 number of elements. With a traditional HP-ROM, we managed to get a 95-mode system of equations with 6,000 number of elements. So the speed up factor here was already of 8, which was good, but not good enough for us. With the new nonlinear mapping, let's just pick the best one, which was the RDF. We managed to get 10 modes, only 1,400 elements, and then we get a speed up factor of almost 50. So we see that we are way better than the traditional HP-ROM. And the good thing is that we are keeping the same amount of relative error as with 95 modes. So we can go ahead and put a much more complicated problem. So this is a flow over a 3D Ahmed body with a fixed slant angle here. And this is a model using half-domain symmetry. And this is a compressible Navier-Stokes problem using 60 meters per second as the free stream velocity. And we use a turbulence model based on the detached eddy simulation with the finite volume method. And the time range is from 0 to 0.2 seconds. A little bit about the mesh. Here we have 17 million degrees of freedom, and we have also 17 million number of elements. And the boundary conditions, just to make sure I am not forgetting anything, is that we have this inlet prescribed velocity. We fixed also the velocity on the outlet to avoid that we have some reflection on the wake. And then we also apply non-slip condition or adiabatic conditions on the walls. And we have a symmetry plane here on the right part. So let us go ahead and talk a little bit about the HDM. As I told you before, this was run in 240 CPU cores and was already taking 10 hours for 2 seconds. So this is something that requires both a lot of time and a lot of resources. So the only thing that we change here, or the parameter in this case, is only the time. We just wanted to show that this problem is independent of the size of the high-dimensional model. But we're not going to select all the training points from the same input parameters. We're just gonna take every 2 snapshots. We will perform the reduction, getting 99.99% of the energy. That already gives us 600 modes for the traditional HP-ROM, which is a lot. This is huge. This is something that you will never build. So with the nonlinear HP-ROM configuration, we built with 39 modes and almost 600 secondary modes. The 39 modes here, I'm going to talk about it later, but we based ourselves in some paper that already use this for the quadratic manifold approximation, so we don't yet have anything to define the n analytically, let's say. And we will perform the training data, or the splitting of the training data into 90% for the training and 10% for validation. And for the HP-ROM element, instead of a depth layer, we have a single hidden layer with LU neurons, which was tested, and it took a lot of effort to do this ANN. More than 100 different artificial neural network, which is one of the things that I'm also against of using ANNs, because it is very difficult to train these architectures, to try to find the best architecture. For the GPR, we use the same maternal kernel, kind of the same function as for the first example. However, for the GPR, we know that the scikit-learn has already some motor inside that does the optimization for you. So for the RDF, we settle candidate kernels, also a bound of the length scale, and we just do a brute force grid search look with cross validation in order to find it, and we will see what we're doing with this. And I will also show that I went even further than 39 number of modes, because I wanted to show that this can surpass what the quadratic manifold can do. For the ECSW, I just want to mention for those that are more or less familiar with the pericalculator method, etc., we only take for every 45 snapshot to get the reduced mesh. So let us go ahead and talk a little bit about the time that it takes to train these methods. So the ANN takes 50 minutes, which is It's a lot, but it doesn't matter because it's offline. For the GPR, it takes now 30 minutes. I just wanted to show you that this is case dependent. But for the RBF, even though it seems like it is the more simpler one, it's a brute force, we still get very good results, and it only trains in 2 minutes. So this is the part that I like about the RBF, is that it has this deterministic component that you can do very easy the training, etc. And if you go ahead and see how many elements we needed for the traditional HP ROM, it was of the ballpark of 8,000. And for the ANN, the GPR, and the RBF, we see that we need less than 10 times what we need for the traditional HP ROM. So only of the ballpark of 500. I'm here also plotting another thing that is called the mesh support elements, or complementary mesh, which is that for each element selected on the finite volume scheme, you will need the stencil elements in order to be able to integrate. And you also, for instance, if you are interested in the quantities, if you have some quantity of interest, like the lift coefficient, you will have to keep all the scheme in order to be able to integrate these quantities. And if we take a look to the one that I was telling you, that I went further down to 10 and 5 degrees of freedom, we see that we need even much less elements, even 72, which is more than 100 times less than the original one. Now, let us go and see a little bit the qualitative results. So I have the drag coefficient time history. As you can see, there is almost no difference in all of the methods. So this is working pretty well. For the element, you can see that at the beginning it does a little bit of something weird, and this is most likely because of the automatic differentiation of the neural network, or the data that was not sufficient for the neural network. And if we go ahead and also plot some isovorticity contours to see that this problem is highly turbulent, we still see that all of the HP ROM managed to get these very tiny turbulence effects. Even for the ones, I'm not plotting here the 145, but it is almost the same. Now, for the quantitative results, we originally have a problem that was 17 million degrees of freedom, or of the size of 17 million. HP ROM now is 600, the traditional one, the other ones are 39. The number of selected elements are way beyond less than the original one. As I said before, the relative error is pretty good for all of them. Actually, it is better for the GPR and the RBF than the traditional HP ROM. And for regarding the wall clock time, so the original HDM, let us recall, it was run in 240 cores. It was taking 10 hours. The HP ROM is only run in 8 cores. It is taking 2 hours, but only in 8 cores. So that means that the total CPU speed up, so the amount, the combination of time and resources, we are already 150 times faster than the traditional HDM. However, if we take a look into the nonlinear projection-based reduced order model with this technology, we see that we can even go around 2,000 times faster than the traditional reduced order model. So what we were solving in 10 hours in 240 cores, we are solving in 10 minutes in 8 cores. So this could be plugged into an edge device. This is one of the things that also needs to be highlighted. If we even go further beyond the n equal to 10, and let us focus more on the HP ROM RBF with size 5, the relative errors are still pretty good, at least from the engineering point of view, is less than 5%. In this case, it's 2.5% error. We are solving the problem only in 2 minutes in 8 cores instead of 10 hours in 240 cores. So this gives us a speed up of almost 10,000 times if you combine the time and resources that you are using. So just to conclude, we were able to introduce an alternative closure, so the GPR and the RBF. They are they scale the same as the ANN. They can be used in the LSPD, and the hyperreduction, it can be also used in Galerkin with your hyperreduction. Can be here I use the empirical. Here I use the energy conserving sampling and weighting, but you could be using the empirical curvature method as well. And it gives a complementary viewpoint that you have a probabilistic way to build this nonlinear map. You have also a deterministic alternative, but both of them are way much more interpretable than the traditional ANN model. So for the accuracy, the Burger's problem, we see that we kind of get the same accuracy both in the performance is the same, both in accuracy in speed and in speed up than the ANN. We always surpass the HP-ROM, the traditional HP-ROM. And for the ARPANET body, we see that we even surpass the ANN performance. And we can see that for the RBF, we went as low as 5. And I didn't include it into these slides, but we show that we can even surpass the quadratic manifold capabilities. So as per the interpretability or the quality or the things of each of the nonlinear closure maps is that for the ANN, it's true that the ANN is highly expressible. However, you need a lot of data in order to train it very well, often. And sometimes I have faced the problem that you need to build the artificial data in order to train it better. For the GPR and the RBF, they both provide analytical expression, which also leads you to better convergence because your problem is often better conditioned, and it provides a probabilistic framework and also a deterministic one that you can make it as efficient as you want. The good thing here, or one of the things that I want also to highlight, is that the GPR and the RBF can operate in very small data sets. So if you have 15 snapshots, it can give you a good extrapolation with 15 snapshots. The ANN will never do so, or it will be very difficult to change that and try to do that with only 15 snapshots. Now, in terms of the hyperreduction, we see that the ANN, GPR, and RBF more or less became the same. It is case dependent, but we always surpass by a lot the traditional HP-ROM. So as per the future work, we need to find an optimal selection of the Lattimer space. So this is now kind of done empirically, and we always want to keep as low as possible the dimension of n. Hopefully, it can yield or it can go as low as the intrinsic dimension of the manifold, which depends on the parameter domain that you have. And the n bar is often selected by some energy truncation of the singular value. You can also select energy truncation on each one of them as another alternative. But we need to select an optimal selection one. An optimal, let's say, artifact or something, or a function that allows for that selection. As per future work related to this also, this is fully compatible with the piecewise linear approximation. So in this case, we can, if the manifold becomes very, very complicated, we can either do a piecewise nonlinear closure mapping, and this is something that I've been working in the past months, and I have not faced real much problems than difference with what you have with the linear piecewise manifold, piecewise linear manifold, and this can enable further reduction in n even better. Now, as per other future work, is that we are now testing this technology also in more complex engineering workflows. We are testing this in hypersonic cases where you have Mach numbers up to 13. So in this case, we can see we're plotting here the stringwise for the stringwise location of x along this bicone at Mach 11.7, the pressure for the HP-ROM with the size of 16, which uses 16 snapshots to generate a 16 degree of freedom problem. With the HP-ROM, ANN, and GPR, we managed to get a degree of freedom of 2. However, for the ANN, it is fair to notice that we had to build 500 artificial snapshots to build it. And it was everything that I wanted to share today. Thank you for coming here. I hope that you enjoy. If you want to have more insights into this work, we already published this in arXiv, and it's being revised already in a so thank you. Is there any question, any comment you want to go further?
Yes, I have.
Yes.
For instance, in the way of that you are trying to select the latent space, like you don't know exactly how to select n and n bar. It's
Yes.
just like an empirical thing.
Yes.
But it cannot be related somehow to the physics of the problem.
Yes, that's why when I said that we want to make this as low as possible, let's say that the manifold often is thought that lives on the dimension of your parameter space. So if you have mu1, one force here in x direction, one force in x and y, and you have time, the dimension of the manifold should be 3. So theoretically,
Yes.
you want to go to that point, but there might be a limitation in what you can do with your data. And that limitation may be well defined with something that is not deterministic, empirical, sorry. So when I said that I want to find an optimal selection, is I want to see how far I can go, but still not losing accuracy. Like I prefer my model to be with 5 modes than to be with 3 modes if my optimal selection says that with 5 modes you're going to have a much better nonlinear map than with 3. You know, so this is the part that it's a little bit empirical, but you are true and you are right that in the sense we try to go with the physics, and that will be going with the physics.
Okay.
So the lower bound will be the intrinsic dimension of the manifold.
And
No,
just one more. And when you have, for instance, when you perform the derivative on the RDF,
yes,
you need the current.
yes.
But is there problems with the differentiability with these functions or not? For instance, the multiquadric is like a square of something. But if
Yes.
you take the derivative, it will go down. So probably you will have a problem of a singularity there.
Yes, okay, yes. So that can be either solved by curing your data or by also regularizing your system.
Yes.
So you will lose some accuracy, and yes, even though it is analytical, you can still have problems with analytical derivatives, but it is less likely that you have a problem because you can do something to avoid that. For instance, if you have in the training data set some points that are very close, or even there are one on top of the other, the problem is already singular. But this will tell you already, like, you can monitorize the condition number of your matrix that you are solving when you are finding the weights, the kernel matrix that you do. This already gives you an insight of your data, if your data is well clean or not. Yes, please.
I mean, this is very nice, and I really like the idea. Now, what I would like to ask you is about what doesn't work, okay? So, a bit of criticism, let's say. Right now, what you did is that you run one example, and then you use the same training data for a check. So what I'm trying to say, you took the unmet body, you set some boundary condition, you set an inlet condition, and you run it.
Okay.
You obtain some snapshot, you compress, and you run the same cascades.
Yes, in that case, yes.
Now, imagine you want to use a slightly different inlet, I don't know, just scale down, or you want to use a different time step. Okay, just not to be exactly the same setup. So same inlet, that's your training, but different. How does it generalize those cases? Do you have any experience?
I have experience both in, so it is true that for the ultimate body I am not doing that. The only parameter is the time. I'm not taking all the snapshots, but still it is reproductive, let's say. But for the Burger's equation, we are testing. So for if I go back to the Burger's equation, and this is already performing some testings. So in this case, the training points is these 9 points, and we have some testing points. And what we are varying here is both the inlet velocity or the starting velocity of the shock wave, and also we are varying another one. So it does generalize it very well. But I also tested for the hypersonic case that I was showing in the end, we are varying the Mach number. So we are testing with 16 different Mach numbers, and then we are varying the Mach number. I also tested with the flow passes cylinder with different inlets, and it was working pretty well.
Okay.
Sorry, just one thing that you asked. I never checked about the time step. Not that I remember.
That's a lot of people report is a problem depending on mathematics in the time step. Just do not make it a multiple.
Okay.
Make it 1.7,
Okay.
1.3, something that doesn't need.
Okay.
The other curiosity I have, when you use the idea, I saw that you presented it in this stabilized form, so you have a lambda.
Yes.
This is just my curiosity, but okay, that matrix is definitely in general not positive definite. So I don't remember how to call that matrix. The one of
The gram matrix or the kernel matrix.
that one is symmetric, but it's not positive definite in general. For example, if you have 2 points of the same, that's singular. So
Yes. So it's symmetric positive definite as long as you don't have to repeat points, and kernels are.
my curiosity in here is why don't you use pseudo inverse for solving it instead of using lambda?
You can use both. In this case, I'm just treating the regularization term as trying to also not only make the problem better behave or better condition.
You got a lambda of 10 to the minus 12, so
Yes.
you essentially switched it off.
Exactly. But you can also do it with the pseudo inverse. At the beginning, I was doing it with the pseudo inverse, but then I just put it into the what I wanted to.
It's a curiosity, I don't know the answer. So.
Yes, you can do it. This could be just the kernel, and this could be defined by beta equal to the pseudo inverse of K. So yes, I have done it as well. Before doing the regularization, I was doing it like this.
And then one last question, and that's a curiosity. For your 3D test case, which you try to approximate by a 2D space, so when you were you have a 3D trajectory and
Yes.
my question is, okay, your manifold only makes sense when you look it and you compare to the points you have.
Yes.
But what is the manifold you would wish to have outside of that? So let's say in the center. I'm just curious. I don't know which one is the one I would wish to have.
For me, we were discussing that before. For me, this is pure hallucination. So this is the rate basis function trying to say this is how it will look like. But
so what does it mean? We would like to be as flat as possible. We would like to be. I simply don't know.
I don't know the answer because I don't think there is like an answer outside the trajectory of how you want yours.
In terms of what I would wish if I was trying to find the closest point. So
Yes.
Which are the properties I would wish to have?
Smooth derivative, I would say.
So they are all smooth derivatives. So
Yeah, don't have
quadrics.
here like a bearish, something in the vicinity that then drops with a huge decay. Because if you are solving this by a Newton-Raphson or something like this, if you are in the vicinity of the point, maybe the farther you go, the less your.
Anyway, I think it would be interesting to have an answer to this.
Yes. Actually, one of the things is, does the physics of the problem can help us with that? That this is where the discrete physics-informed training that we were doing before may help. Because if you are on a training point, this is for the trajectory, and you want your trajectory to be held well in the vicinity of the. At least you maybe want to behave it well in the physics sense. Yes, this can be analyzed like this.
There is a very short one. So it's about the RBF. The results you showed are for the optimal selection of the epsilon parameter of the RBF. So my question is how sensitive it is to the choice of the epsilon? And besides this, what is your strategy to select? Because suppose you said, okay, take epsilon from 0.205 and then I 2.4. Why 2.4? How do you get it?
Okay, so the way that I get it I think on the RBF is more, it's easier to understand, is that you do a grid search, you have epsilon, which is the shape of your, and then you do a simple square domain where you have epsilon, you define your bounds of epsilon, and for instance here you have your kernels. They make the Gaussian, the inverse multiquadratic, and then you perform a grid root search and go through all of the points that you want, and then you measure how well your data is trained, and then you pick the point that has the minimum error with all of the combination. This is the simpler case. However, that's where
the parameter space of this problem that you are.
yes, but if you use the GPR, which is using as a motor of the interpolation, the RBF, then there is a probabilistic model that minimizes this marginal likelihood function that gives you some sort of idea of where to go in order to find the proper. But then in here you need to fix the kernel, and then it will select the epsilon and whatever you else have. So this is the good thing about the GPR. Actually, as you can see in the following slide, at the end of the day, what we use for our nonlinear map is exactly the same.
Yeah.
So the GPR gives you an RBF at the end, but the way that it is trained is one is trained brute force, or can be trained even better, and the other one is often trained with this, but it can also be trained brute force. So it was very difficult in the paper to differentiate these two, because at the end of the day they are the same. Actually, this is one case of the Gaussian process. So if you don't want to, if you turn off the probabilistic part,
You get the other one.
you are using RBF.
Understood. Thanks, Sebastian. And congratulations.
Thank you. Does anyone have any other question? If not,
Thank you.